Here are the big purposes and look fors for simple machine and work. First, we're going to real quickly go over the 6 simple machines. We're going to talk about what work actually is and why that is nice for us. We're going to talk about how machines impact us. And we're going to talk about mechanical advantage and some numbers to look out for. So you probably know a lot of simple machines right off the bat. So the way that we kind of define these simple machines are just these easy little mechanisms that are going to mess with the force and distance required to move something. And we've simplified it into 6 little categories. The first one is a lever. So if you think of like a teeter-totter or like your seesaw, nail clippers are good examples of levers. We've got wheel and axles. So here's our wheel. We've got a little tiny axle in the middle. We've got pulleys and pulley systems. So that's what we're using to lift our plane right there. We've got an inclined plane going up the roller coaster hill. If we turn that to the side, a wedge is super similar to an inclined plane, so something like an axe. And then a screw is the last of our simple machines, kind of a combination of our levers and our inclined planes. And you've probably messed with these plenty of times, but never really thought about what they actually do for us. So simple machines manipulate variables inside of what we call work. So if you go into a physics class, work is essentially like evidence that energy is being exerted. But in engineering, we can whittle it down to a force times a distance. And we don't need to calculate anything, but we can use this as a nice little reference to talk about how this stuff is happening. So if I have a box and I have a required amount of force needed to move the box, I would take that amount of force I need to push times the distance that it travels, and that would be my work. So if I push harder with more force, that requires more work. If I push it a farther distance, that requires more work, right? We don't need to calculate it. We just need to know kind of how this stuff works. So let's say that you're trying to toss this bike into a truck. So think about some different ways that you can perform that action. The first one, probably the dumbest one, is you can just do it yourself. You can lift it up. Now, keep in mind, work does not necessarily mean like effort. Work is how much energy is exerted in order to perform the task. So think of it like this. I need to get that bike from the ground up to that tailgate, right? That is my distance. And it's actually a pretty small distance. However, in order to do that, I need a huge amount of force to make that happen. So small distance, big force, which is not good for humans. But we can change that. We can use a machine. So this is our inclined plane, right? I make a little ramp to push that up. So now all of a sudden, my distance is huge comparatively, right? I've doubled or tripled the amount of distance I need to push it into that tailgate. However, what I do is I need a little teeny tiny amount of force to actually make that happen. So again, notice we're manipulating distance and force. And maybe the last one, you have like a weird pulley system that you set up. So you are required to pull that object for a long distance. Maybe you have to tug on the rope a long time. But the benefit you get is a little tiny amount of force required to do that. So at the end of the day, what simple machines do for us is they don't actually change the amount of work, but they do make the work easier. And typically we want force to go down, which means our distance are probably going to go up. So kind of think of it like this. If your work is always constant, no matter what simple machine you use, you can decrease the distance if that's a priority, which increases your force. Or if you use a ramp, you can increase the distance that it moves, and that will decrease the amount of force you have to actually put into it. Same thing happens when you're riding a bike. So if you go to a higher gear, it's really hard to pedal. So you have a high amount of force, but you don't have to pedal as much to go the same distance. On the flip side, if you gear down, it's really easy to pedal, but you have to pedal many times to get that same distance. So your amount of work is always the same no matter what. Simple machines just prioritize distance or force to either make it easier in terms of force or shorter in terms of distance. And that's what leads us to mechanical advantage. So this is how we actually provide ratios of advantage. So a mechanical advantage is essentially the ratio of the resistance force, which is usually your object, compared to your effort force. So how much force do you put in to lift an object? We can also think of it as the distance that you need to push, which is your effort, compared to the resistance. How far is that going up? So we had to push it a long ways up a ramp to make my resistance go up to the tailgate. So think about when you are designing machines, do you want less force required or do you want less distance required? Because there's always drawbacks based on work. So if we look at this inclined plane and we say we have a mechanical advantage of 4-to-1, what that tells us is that I need to put in 4 times less effort to lift the resistance force. Meaning, if I had a box that was 4 pounds, if I use a ramp with a 4-to-1, then I only need to put 1 pound of effort to make that thing move, right? Think of it as like magnifying the effort force. On the flip side, your distance goes up. So if my force goes down, I have to push it 4 times greater than what I would normally. Now for mechanical advantage, 1 is the magic number, right? So 1 tells you if you're getting an advantage or not. So if it's bigger than 1, that means you put in less force to move an object. But the trade back according to work is you have to push it a greater distance. If you have a mechanical advantage of less than 1, then you have to put in more effort force to move an object, but you have less distance. If you're right smack dab at 1, then there's no advantage one way or the other. So it can never be less than or equal to 0. So it's only less than 1, 1, or greater than 1.